Hello, my name is David Ruth, and my poster is about the g2p experiment, which is a measurement of the proton spin structure in the low q squared strong-QCD regime. So the proton accounts for a vast majority of the visible matter in the universe, but we still don't totally understand it. Originally, it was believed to be a point particle, but nowadays we understand it to have a complex dynamic structure of quarks and gluons. Of special interest is the spin of the proton, which has motivated a number of recent questions about how that spin is distributed and how the proton derives its spin from its constituents. So we can actually access information about the proton spin structure through quantities called structure functions. With inclusive electron-proton scattering, a polarized electron beam, and a spin-polarized proton target, we can expand our cross-section in terms of these quantities g1 and g2, which characterize the spin structure of the proton. These structure functions are very important for understanding QCD, especially in the long-distance low q squared regime. One of the best low q squared theories available right now is chiral perturbation theory. But chiral perturbation theory has struggled to reproduce neutron data at low q squared over the last 20 years in something known as the delta LT puzzle. Delta LT is a moment of these structure functions, and it was considered an important benchmark because it is insensitive to contributions from the delta resonance. So because neutron data has disagreed with chiral perturbation theory at low q squared so much, it's important to see if this issue exists for the proton as well. So this is the experimental setup of g2p. Electrons are scattered off of a spin-polarized target, ammonia target, polarized with a technique known as dynamic nuclear polarization. And then the scattered electrons are measured in the Hall-A high-resolution spectrometers. So how does this dynamic nuclear polarization work? Well, polarizing electrons is easy. When you apply a strong magnetic field, in this case 2.5 or 5 Tesla, you get more than 99% electron polarization. But protons are much more massive, so they're much harder to polarize. So what we do is we stimulate a hyperfine coupling by applying microwaves tuned to the energy level gap displayed here, which causes electrons to drag protons with them when they polarize. And then the electron relaxes much more quickly, so a single electron can drag many protons to polarize. So to actually measure G2, we want to look at these quantities called asymmetries, where we compare forward and backward helicity scattered electrons and look at the cross-section for each. With these asymmetries and an unpolarized cross-section, you can form polarized cross-section differences, which are related to the structure functions G1 and G2. And because there's lots of world data on the longitudinal structure function G1 and on unpolarized proton scattering, we can use models for both and solve for G2, which is of our interest in this experiment. So these are our results. On the top, you can see the final results for the G2 structure function. And on the bottom, two of its important moments. On the left is delta LT, where you can see the data actually agrees quite well with one of these calculations of chiral perturbation theory and disagrees a fair bit with the other one, which makes it important to resolve the difference between the two calculations. The other moment, D2, helps to study the quark-gluon correlations of the proton, and here we also demonstrate good agreement with the calculations of chiral perturbation theory. So this data, the analysis is complete, and our first paper is currently under review for publication in the journal Nature Physics, and we hope that that will be published quite soon. So that's about all I have to say. Thank you so much for your time.